Hey everyone, and welcome. Today, we're diving into a chemical technique that's so precise, it's almost perfect. And you know what? The secret sauce is just weighing something. Seriously, it's called gravimetric analysis. But first, let me ask you something. Think about a pill you might take, or even a glass of tap water. How in the world would you figure out the exact amount of, say, the active ingredient in that pill, or maybe one specific mineral in the water? I mean, down to the tiniest fraction of a gram. Sounds kind of impossible, right? Well, that's where this really cool, classic method comes in. It's called gravimetric analysis. And the whole idea is, you take that complicated mixture, you find a clever way to pull out the one single thing you're interested in, and then you just weigh it. That's it. At the end of the day, it all comes down to its mass. So you're probably wondering how this all works, right? Well, here's the plan. We're going to cover the basic idea, then get into the nitty-gritty of the separation process, check out the different types, and finally, look at the good and the bad.
All right, let's jump right in. The main idea behind this whole thing is actually super simple once you get it. Let's use a little analogy to make it crystal clear.
Okay, so picture this. You've got a beaker with a mixture of 3 different chemicals. We'll just call them A, B, and C for now. They're all just mixed up together in there. And your job, your mission, is to find out exactly how much chemical B is in that beaker. We don't care about A, we don't care about C. We are laser focused on B.
Now, in chemistry speak, B is what we call the analyte. That's the thing we're analyzing. And that means A and C, well, for our purposes, they're just impurities. They're getting in the way. So the whole game is this. To get a super accurate weight of B, we have to get it completely by itself. We've got to isolate it perfectly.
Okay, so how do chemists pull this off? How do they actually do this tricky separation? Well, this is where it gets really cool. It's not magic, but it's a super clever step-by-step process.
Okay, this might look like a long list, but it flows really nicely. First, you dissolve the whole mixture in a liquid. Easy enough. Then, and this is the key part, you add a special chemical, a reagent, that's designed to react only with our target, chemical B. And that reaction turns B into a solid, so it literally falls out of the liquid. We call that precipitation. After that, you just need to let those solid bits get a little bigger, filter them out, give them a good rinse to wash off any leftover A and C, and then dry them out completely. And the last step? You guessed it. You put that pure, dry, solid B on a scale and weigh it. Boom, that's your number. But hang on, let's talk about step 3 for a second, digestion. And no, it has nothing to do with lunch. This is basically a patient waiting game. You let the solution sit for a while, maybe warm it up a bit. What happens is that the tiny, messy solid particles actually dissolve and then re-stick onto the bigger, cleaner particles. It's like they're tidying themselves up. And why do we do this? Because bigger, cleaner particles are way easier to catch in a filter. It's a clever little trick to make sure you don't lose any of your sample, and it's a huge reason why this method is so accurate. So, that whole turning it into a solid thing we just walked through, that's the most common way, for sure. But this basic idea of separating and weighing can be done in a few other ways, too. Let's quickly run through the 4 main methods.
So we've got precipitation, which we know all about now, but then there's volatilization. Think of it like this. You heat a sample to find out how much water is in it. The water turns to steam and escapes, and the weight you lost tells you how much water was there to begin with. Pretty smart. Then you have electrogravimetry. This one's cool. It uses electricity to stick a metal, like copper, onto a plate. You just weigh the plate before and after, and the difference is how much copper you had. And lastly, there's thermogravimetry, which is basically weighing something continuously while you heat it up to see how it changes. Okay, so it's pretty clear this is a super powerful and crazy accurate technique. But, nothing's perfect. Like any method, it has its pros and cons. Let's talk about the big trade-offs here.
And this really lays it all out. On the plus side, you get accuracy that is just off the charts. It's so precise. And since you're just using a scale, there's not much that can go wrong with fancy equipment. It's also pretty cheap. But here's the big downside. Man, is it slow. It takes a ton of time and careful work, and you're usually just analyzing one single thing at a time. It's the complete opposite of all the fast automated machines we have today. But that incredible accuracy, that's precisely why it's still so important. This method is so trustworthy that it's actually considered a primary standard. What does that mean? It means scientists use it to check if their other, faster machines are working correctly. It's the benchmark. When you need to know the exact right answer, no questions asked, this is the gold standard you turn to. I mean, think about this. It's been used to figure out the atomic masses of elements to 6-figure accuracy. That's just wild.
So that kind of leaves us with a bigger question to chew on, doesn't it? In our world, where everything is about speed, automation, and getting things done instantly, what's the real value of a slow, careful method that guarantees you'll get it right? It's definitely something worth thinking about. Thanks for diving into this with me today.